Hello, students of science. In this video, we're going to talk about gases and pressure. First off, let's talk about pressure. So gas molecules are going to exert a force against any surface or container in which they collide. In this particular example here, we have all these molecules of a gas bouncing around. Every single time one of these hits the wall of that container, it's going to be exerting some pressure. The fact that you don't feel the individual particles is for a few reasons. One, they're small. Two, there's a lot of them, like on the order of quadrillions and quadrillions. And three, they're hitting it very, very, very fast. So you will not feel the individual particles hit it. What you're going to be feeling is essentially quadrillions and quadrillions all hitting at the same time. You're going to feel that as pressure, like a balloon that's inflated. You will feel the pressure of it pushing out. Just like this, only, a lot more and a lot faster, and they're a lot smaller. Pressure is the force per unit area. So the SI unit is pascals, force of course is newtons, and the unit area is meters squared. So we have force pushing down on an area. If we have that same amount of force on a smaller area, that is going to result in higher pressure. Atmospheric pressure is essentially going to be the weight of gases in our atmosphere pushing down on us. And if they're on a smaller area, it's going to be a higher pressure. Think of it as all these different gases, this massive, massive column stretching up to space and beyond. All of those are gas particles. All of those are affected by gravity and they are pushed down. The closer you are toward the ground, the higher the air pressure is right there. But that's what air pressure is. All of the gas in the atmosphere pushing down. The atmosphere is about 78% nitrogen, 21% oxygen, and 1% other gases, all of them squishing down on us. The reason we don't feel it is because we got a lot of stuff on the inside that's pushing back out as well. So here's more of the atmospheric pressure. Just imagine a column of air stretching up all the way to space. It's got a lot of mass, 10 to the 4th kilograms. That's a lot of mass. All of that pushing down is going to be experienced as 1 atmosphere of surface pressure. The reason that you're going to feel less pressure when you go up higher in altitude is that this giant column gets smaller. You go up to 18,000 feet, a really tall mountain there. Essentially, you're still getting air and all this stuff squishing down on you. It's just that this column, this container here, is going to be a lot shorter because it's not including all the stuff underneath it. So higher pressure right here as opposed to at higher altitude because this container, quote unquote, is smaller. So we measure pressure in a couple different ways. Number one is going to be a barometer. You may be familiar with it. A barometer is going to measure the atmospheric pressure, how much that gas is pushing down. And the way it works is air is going to push down on a column of mercury and it's going to push it up into a tube. So you start with a completely filled tube of mercury, sort of put your thumb over the end of it. Also, don't touch mercury with your thumb. Maybe a glove or a lot of gloves, and you essentially turn it upside down and put it in a bowl of mercury. Now, what happens, of course, gravity is going to pull it down, but it's only going to pull it down so far because air is going to be pushing down against that, trying to push it back up. How far it goes down determines the pressure. The higher or lower the mercury goes, the higher or lower the air pressure. The reason this is really important to us is because when you have a storm coming, that's going to start causing some big changes in the air pressure, either higher or lower depending upon what's happening, but that does give you a clue as to what's about to happen. So here we have another atmospheric pressure. Basically, a barometer up here is going to measure a lot less pressure because there's a lot fewer gases pushing down against the mercury. All the way down here, a lot more gases are going to be pushing down. By the way, the reason you use mercury as opposed to something else is the fact that mercury is so incredibly dense, 14 times denser than water. A cannonball thrown into mercury, don't play with mercury kids, would actually float because it is so dense. If you were to use this with water, you technically could. It would just have to be 14 times higher, and that's a little bit unwieldy to work with. Another way we can measure pressure is with what's called a manometer, not a manometer. Manometer, it measures the pressure of a gas sample instead of the atmosphere. So it's like a barometer, but we're not measuring air pressure. In this case, we're measuring the pressure of a sample of gas. So here's a manometer right here. Here is our sample, and it's going to be doing the same exact thing. It's going to be pushing down on a tube of liquid, probably mercury, and we're going to be looking to see how much space is left there. Higher pressure gas, the more it's going to push against that, and it's going to push that up. So here our sample pushes down, and it tries to push the liquid further and further up the tube. The more pressure there is, the higher it goes. Less pressure, more down it goes. When we're measuring pressure, we've got a couple different units. So 1 atmosphere of pressure is equivalent to, well, 1 atmosphere, duh, but also 760 millimeters of mercury, mmHg, or 760 torr. I will use those interchangeably because they're essentially the same. And remember, this is a measure of how far it can push that mercury up. In the case of our barometer, 760 millimeters. Here we can see we have a pressure gauge. This one is measuring in millimeters of mercury. That's also equivalent to 101.325 kilopascals, not pascals, kilopascals. So that's 101,325 pascals, or 14.7 psi. You see that a lot in America, but that is not an SI unit. It's not metric. I'm not going to be using that one much. What you will see, and I will always give you this on a test or on a quiz or anything else like that, we are going to be seeing all of these right here. All of these are equivalent. You can use these with dimensional analysis to figure out and convert between units. 1 atmosphere, 760 millimeters of mercury, 760 torr, remember equivalent torr in millimeters of mercury, 101.325 kilopascals, or 14.7 psi. All of those the same, all of those equivalent. Here we have another pressure gauge. This one has both kilopascals and psi. These are common units. Anytime you are doing calculations for volume, you need to include both temperature and pressure. So that's very, very important that you include those because those will affect the overall volume. More on that later. But what we're going to use is what's called standard temperature and pressure. You will see it abbreviated STP. No, not the oil brand. Yes, I'm aware that's a thing. But standard temperature and pressure is 1 atmosphere of pressure in 0 degrees Celsius. Super, super, super important that you know this. Standard temperature, 0 degrees Celsius. Standard pressure, 1 atmosphere. Partial pressure in Dalton's Law. In a gas mixture, each gas is going to exert its own partial pressure on the container. Remember, each of those molecules is going to be punching against it. Kind of makes sense. Dalton's Law says that the total pressure is the sum of all of the partial pressures of each gas in that mixture. This is one of those things that kind of like, did they really need a law to explain that? They do, because when you're collecting gas over water, you have to account for the water as well. So that comes into play a little bit. Here we have a sample. Gas A is going to be exerting a pressure on this manometer of 300 millimeters of mercury. Gas B is 400 millimeters of mercury. If we were to combine gas A and gas B together, Dalton's Law says it's going to be the sum. 300 plus 400 is going to give you 700 millimeters of mercury, and that's what we see here. The manometer is pushed higher here because it's a combination of both A and B. Dalton's Law specifically is written out as PT, that's, total pressure. It's pressure of 1 plus pressure of 2 plus pressure of 3, however many gases you happen to have, all of those add together. In a sample of air, there is a partial pressure for all the different gases we have. Oxygen is going to do a partial pressure of 20.9 kilopascals. Nitrogen, of course, is the most abundant gas in our air, is going to be exerting the greatest pressure. Argon, just a little bit. Water, just a little bit. CO2, just a little bit as well. But all of those are going to add together because of Dalton's Law to come up with the pressure we have of air at 1 atmosphere of pressure, or 101.3 kilopascals. Dalton's Law, it's just the sum of all of these. Here I have a gas sample here, 100 kilopascals. That is going to be the sum of, well, just the red ones. There's going to be exerting a force of 40 kilopascals, blue 60 kilopascals. When you add those together with Dalton's Law, you're going to get 100 kilopascals.